All right, I'd like to welcome our next speaker, David Rosenthal from St. John's University, who will tell us about finitely F-amenable actions and decomposition complexity of groups. Take it away, David.
Can you hear me?
Yep, sounds good.
Okay, let me. Okay, well, thank you very much to the organizers for the chance to speak at this really nice conference. What I'd like to talk about today is joint work with Andrew Nicas from McMaster University about a condition, finitely F-amenable actions that's been used to prove Farrell-Jones Conjecture for many classes of groups and related to decomposition complexity of groups, which is a coarse notion that is a generalization of finite asymptotic dimension. So the story begins with Guoliang Yu's result, where he was able to show that if you have a group that has a finite CW model for BG and finite asymptotic dimension, then the Novikov conjecture holds for G. And this sparked widespread interest in finite asymptotic dimension, which was defined by Gromov. So just to remind you that definition, so it's a large scale analog of covering dimension and was introduced to study groups. But we start with the metric space X and say the asymptotic dimensions at most n if for every R you have the following two conditions. So you can decompose your metric space into pieces. So it's often phrased in terms of colors. So you have n+1 colors, and within each color, you can further break down the pieces into R disjoint sets. Such that the collection of all those smaller pieces is uniformly bounded. And this has already been mentioned, I think, a couple times in the conference, but just to show you a couple of the easy examples. So the asymptotic dimension of the reals is actually equal to 1, but to prove that it's less than or equal to 1, you just use this picture. So given your R, you need two collections of two colors, and you split them up into these intervals so that you have the R disjointness property and, of course, the uniformly bounded property. For R2, the dimension is 2. To prove that it's less than or equal to 2, you can use this picture with these bricks, where you take bricks with 3R and height 2R, and then you color it this way with 3 colors, and that guarantees that you have the separation property. What turns out to be true in general is that the asymptotic dimension of Rn is equal to n. And there are various ways that additional spaces and so on can be shown to have finite asymptotic dimension by using inheritance properties that we have, and that'll be a theme that comes up. So this isn't part of the world of coarse geometry, which was very nicely explained in the previous talk. And just to remind you of some of these definitions, so we have the types of functions that we're focusing on are coarse. So balls of radius r get sent to balls of radius rho of r, which is, so this rho is a non-decreasing function that is sometimes called a control function. And so you have these chunks being moved, and then coarse maps are called close if you have a uniform bound on the distance between the images of points. And then you can define coarse equivalence, or F is a coarse equivalence if you have a coarse map coming back so that the compositions are close to the respective identities. And then one way to define the coarse embedding is to say that it's a coarse equivalence from X to a subspace of Y. And asymptotic dimension is a coarse invariant. So coarse equivalent metric spaces will have the same asymptotic dimension. Subspaces have asymptotic dimension less than or equal to the larger space. And so this tells you that in particular coarse embeddings from X to Y means that asymptotic dimension of X will be less than or equal to the asymptotic dimension of Y. And then you have these other nice properties that come up and you can use from smaller pieces getting more information about other spaces that are more complicated. In particular, talking about groups. So if you have a countable group and a proper left invariant metric, then the asymptotic dimension of the group is defined to be the asymptotic dimension with respect to that metric. The point here is that if you have any two proper left invariant metrics on a countable group, then those two metric spaces will be coarsely equivalent. So if it's finally generated, then you're taking the word length metric. But if it's not finally generated, you need a so-called weighted word length metric, and I'll give you an example in a moment. And as you can see, it behaves nicely with respect to extensions. This theme of these permanence properties is something I'll come back to as we generalize. So as was mentioned in the previous talk, Zn is coarsely equivalent to Rn. And so we know that the asymptotic dimension of Zn is n. And of course, one immediate consequence of that is that if you have a group that has a Zn subgroup for every n, then the asymptotic dimension of that group has to be infinite, right? Because it has to be bigger than or equal to n for every n. So having finite asymptotic dimension tells you something about the Novikov conjecture. And one of the goals here is to sort of expand that to more groups, well, in particular groups with infinite asymptotic dimension. So one group which has infinite asymptotic dimension, obviously, is the countable sum of z's. And this is an example of a proper left invariant metric, and it's one of these weighted word length metrics to make sure things are spread out as you go out. A finitely generated example of something with infinite asymptotic dimension is z reads z. Of course, it has the previous group as a subgroup. So Guttner, Tesser, and Yu were able to generalize the definition of finite asymptotic dimension, and they did so by generalizing the notion of metric space and coarse geometry of metric spaces, and they extended it to so-called metric families. So metric family is just a set of metric spaces. If you want to study a single metric space, then you look at the set containing that single metric space, that singleton set. A subfamily, so a metric family is a subfamily of another one if every element is a metric subspace of some element of the bigger one. So one example to keep in mind here is if you have a single metric space and then you have X is the singleton metric family containing that metric space, and Y is a cover of that metric space, then that cover will be a subfamily of X. We say that a metric family is bounded if the diameters of all the metric spaces there are uniformly bounded. We sort of drop the word uniformly, even though all these things have to be done uniformly. Otherwise, you have uniformly showing up in too many places. So we say that. So before we were talking about the uniformly bounded covers, that would be an example of a bounded metric family. And then we generalize the notion of maps and coarse maps, and coarse embeddings, and coarse equivalences to this setting. So the key thing here is a map is a collection of functions between the metric spaces in X and Y. The one rule is that you have to have at least one function for every metric space in X. And then you look at the previous definitions, but you do it in this uniform way, meaning that so if you have a coarse map or map of families, then every function in there has to be coarse like before, but with the same control function. Okay. And then you generalize the notion of coarse embeddings and coarse equivalence in similar ways. Okay, so now this generalization of finite asymptotic dimension. So we say that a metric family, and if you want to think of just a single metric space, it's fine. Here, you n decompose over a collection of metric families if for every R, you have something similar to those previous two conditions. So you can decompose each metric space with these n+1 colors, such that within each color, you have these smaller pieces which are R disjoint from each other. But now we relax that next condition about the uniformly bounded part. We say that the collection of all these Xij's has to be a metric family in this collection C. So the idea is that this collection C will have some property that you're interested in, and then you're decomposing over that. So if you take the collection to be the collection of bounded metric families, you come back to finite asymptotic dimension. here with this definition with metric families, Bellinger-Nishnikov defined uniformly at finite asymptotic dimension previously. If you take a single metric space here, or the metric family with a single metric space, you just get the previous definition of Gromov. Okay, I mentioned permanence properties. Here are three that are mild, turn out to be very mild properties that you would like your collection of metric families C to have. So if you're talking about coarse things, you want it to be invariant under coarse equivalences. And so coarse permanence here says that if you have a metric family which coarsely embeds into one in your collection, then X has to be in there. And then we have two types of finite unions here. The finite amalgamation is if you have finitely many metric families in your collection, and now you just sort of dump them all into one big set, then that larger metric family should also be in the collection. And another way you could build unions out of finitely many metric families is you create a new metric family where each metric space in there is made by taking a union of one metric space from each of the finite collection that you have. And so that should also be in there. And as I said, these are mild. I'll give some nice examples of common collections that we'll discuss, for which all of these are satisfied. And there are lots of other permanence properties, as I said, that's used to establish lots of results about groups, right, which is the ultimate goal. But these three mild ones are ones I want to talk about in the theorem with Andy. Okay, so here's a list of collections of metric families, very ones that appear a lot, and they all satisfy these three basic permanence properties I mentioned. So the first one, bounded metric families, has this property. The next one here, metric families with asymptotic dimension at most k. So the k is fixed, and look at anything less than that. And the one below that is metric families with finite asymptotic dimension where you don't specify the k. D and WD, these are so-called strong and weak finite decomposition complexity. These collections are the ones that were defined by Günther, Tesser, and Yu. It's actually easier, more natural to define the weak FDC one. So that's where it's the smallest collection of metric families that is closed, that contains the bounded ones and is closed under N decomposition. So if you N decompose over the bounded ones, you get finite asymptotic dimension collection. But then if you do that again, you leave the world of finite asymptotic dimension. And so these, you just collect all those. And the thing is, it turns out the techniques for working with finite asymptotic dimension in terms of proving Novikov conjecture will still hold, still go through. And, the strong one is where you're restricted to have two colors at every step, at most two colors at every step. And that's for technical reasons with certain types of rigidity problems, theorems they wanted to prove. The next one is exact metric families. This is related to property A. And then the final one there are metric families that coarsely embed into Hilbert space. As you go down the list here, each one is contained in the one below it. And any group that's contained in here, in any of these, will satisfy the Novikov conjecture. In terms of N decomposition, by definition, the weak FDC, that collection is closed under N decomposition. That's how it's defined. But the only other two on this list that are closed under N decomposition are the exact metric families and the ones that coarsely embed into Hilbert space. I should say here, it's unknown whether it's an open question whether or not the strong and the weak forms of finite decomposition complexity are in fact the same thing. Okay, so just some basic examples specifically focusing on finite decomposition complexity. So that countable sum of z's example, that you can show that zero decomposes over the collection of metric families with finite asymptotic dimensions. Nice little example. The point is that the dimension, that finite asymptotic dimension metric family that dimension depends on the R you started with, so it's growing as you're doing those, as you're checking those steps. That argument can be generalized to show that these collections are closed under countable direct unions of groups, and we also have that they're closed under extensions, so you get lots of nice groups going into there, including the Z re Z. And because of those two properties being closed under countable direct unions and also extensions, gives you that they contain elementary amenable groups. And these linear groups are one of the key examples that they focused on. Okay, so this notion of an NF-amenable action, it was introduced by Bartels, Lück and Reich when they were studying or proving that word hyperbolic groups satisfy the Farrell-Jones conjecture. They didn't frame it exactly this way. This was sort of repackaged by later work of Bartels. But it was definitely inspired a bit by finite asymptotic dimension. So here we start with a G space and a family of subgroups. And we say that an open cover of X is an F cover if it satisfied two conditions. It's G invariant. So as you translate elements of the cover around, you get another element of the cover. And the only way a group element can leave an element of the cover invariant is if it's an element of one of the subgroups in the specified family. Otherwise, it moves it off it completely. And then we say that the action is NF-amenable if for every finite subset of G of the group, you can get an open F cover of G cross X. Here you're looking at the diagonal action, such that the dimension of the cover is bounded by N. And you have this so-called S-wide condition that as you, for each X, you can find an element of the cover that contains the width S cross X. And these were able to, this then can give you certain maps to uniform simplicial complexes that can be used. And the key thing here for applications is when X is compact and metrizable. The easiest example to draw something is one with Davis, Quinn, and Reich for the infinite dihedral group, which is a nice one. So I include this little picture and invite you to look that up, where this gives you a two-dimensional cover, and the subgroups of the infinity that you're looking at are the cyclic ones, so the infinite cyclic group, and then these conjugates of Z2. And you can see that this one will generate to you by pulling back to D infinity cross R bar. Here R bar is that 2-point compactified real line. Of course, you see here, this only will help you with very small s, and the width is small, but you can stretch this out depending on what S you need and pull it back. So very nice, really the only hands-on example that I'm aware of. Okay, so they use this to prove Farrell-Jones for hyperbolic groups by showing that its action on the boundary is finally V-sic amenable. Here's the inversely cyclic family. And then this was extended by Bartels for relatively hyperbolic groups later on. Bartels and Besvina have recently shown that mapping class groups satisfy the Farrell-Jones conjecture. And in that work, they formalized a hierarchy of groups using this notion of NF amenability. So what they did was they start with a class of groups that's closed under isomorphism, taking subgroups, and then they look at the groups that admit a finally F-amenable action. So for some N, it's NF amenable on a compact Euclidean retract. And then they look at the next step, right? So now they look at NF amenable actions over AC of F, and so on. They build this hierarchy. And what they showed was that all groups in acvnil, so here V-nil is a class of finitely generated virtually nilpotent groups, that all of these will satisfy the Farrell-Jones conjecture. And in particular, they'll be able to capture mapping class groups and surfaces in this collection. What I was able to do with Andy was to say that if you have a group that admits an F-amenable action on a compact metrizable space X, so not Euclidean retract, you don't need that part. And if you know that every element of your family belongs to some collection C that satisfies those three mild permanence properties, then your group G will n-decompose over that collection. In particular, if the collection is closed under n-decomposition, then G will be in the collection. And so applying this to Arthur's result about relatively hyperbolic groups says that if you have either the weak finite decomposition complexity, exact metric families, or the collection of ones that embedded, coarsely embedded to Hilbert space, if you're relatively hyperbolic with respect to groups that are landing in there, then G will also land in there. And this is a generalization of a result by Osen, who first studied some things like this, where groups find asymptotic dimension. There are other authors who have similar results. What I'd like to end with is this other corollary about this collection acvnil. So the other application is that any group in there has to have weak finite decomposition complexity. And so the reason is the finitely generated virtually nilpotent groups have finite asymptotic dimension. So this means that this family, all the elements of the family are in this collection A, right? Finite asymptotic dimension. But then if you're an acvnil, little acvnil, that means you're NF-amenable over vnil, or with respect to vnil. And so that means that from my result with Andy, that you're n-decomposable over the collection of things that have finite asymptotic dimension. Well, that says then, in particular, that it's contained in the weak finite decomposition complexity collection. But then to build the next stages, you're just n-decomposing then over that same collection over and over, but the WD, this weak finite decomposition complexity, is closed under n-decomposition, so you never leave weak finite decomposition complexity after that. One of the implications of this is that this collection acvnil, it can't be closed under directed colimits. There's an example of Gromov, which is a directed colimit of hyperbolic groups, which can't coarsely embed into Hilbert space, and so it can't be in here. And so that's it. I'd like to just leave the last slide with a couple of open questions about cat-0 groups, which is one of the motivating problems for us in general. So it's peculiar in a sense to know that cat-0 groups are known to satisfy Farrell-Jones conjecture, but we don't know if they have finite asymptotic dimensions. So they don't fit into this NF-amenable framework as yet. And in fact, we don't even know if they land in one of these other classes. Thanks. Oh, can't hear you, Craig.
That explains the blank looks. Sorry about that. Any questions for David?
Could you share the the Bartel and LR condition, that this slide one more time?
This one?
No, earlier. Bartel and two other.
Oh.
Yeah, what is the meaning of, I mean, you wrote what it is, but is there can you say in short, what is the meaning of this condition?
Well, these produce these these covers then produce uniform simplicial complexes and maps to them that have a strong control condition with them, which allows you to do tricks in K theory, right? So Farrell-Jones conjecture, Novikov conjecture, these become statements about certain K theory groups. And one of the techniques is to kill certain obstruction groups that come there, and these controlled maps that give you a lot of power there to do that. And so that was that idea goes back to Guliang's initial result, his proof, where that's one of the things he did there within the world of Baum-Kahn. But that's these shrinking maps play a major role. And so this was the idea here, I think, was to sort of make an equivariant version of that in some sense. Yeah.
So this moving U off, I mean, the image of, so GU moving it off U, is it similar to the dynamic asymptotic dimension condition, or?
Yeah, no, that's a good question. Yeah, there's a relationship there. So, so the dynamic asymptotic dimension condition, they don't need, and they're also looking at compact spaces, but not ones that are Euclidean retracts. That's not one of the forced upon conditions, but there, I believe the finite dynamic asymptotic dimension condition would be corresponding to the family of finite subgroups here.
I see.
Specifically. And yes, they map out that connection, and it's a very interesting one. And again, so that in particular the invariant condition and the F subset condition, right? When you take the nerve, that's going to give you that the stabilizers of points, of vertices, right, in the cover are going to come from the family, right? That's where that shows up.
Thank you.
Hey, David, I don't want to get off topic, but if you have time to stick around after this last talk, I actually have questions that are just peripherally related to this.
Sure.
If you're busy, I understand, but
No.
Okay.
I'm here.
Okay, so let's talk after this next talk, but we've got just a few minutes before the next talk, so let's thank David for a really nice talk. All right, we'll begin again with the final talk of the workshop.